All right. Good evening, everyone. Hi, Amit. Able to? Okay. All right. Sure. Good evening, Amit. I think only we two are here today. Uh, so, what I'm going to do today is I'm going to cover week 7 content about gas mixtures. We will solve few problems about week 7 content. Um, so, before going forward, do you have any questions, Amit, you wanted to ask me?
Actually, sir, I do. With the lecture 17, last problem, and it's the last part where we solve the pressure for with additive pressure rule.
I see. Okay.
Yes, sir. In this problem, I want to know how we calculated the reduced volume here, but
Mm-hmm.
the specific molar volume for the component one, I want to know how it was calculated because the formula that was shown on the screen was V by N1. I am not sure which V it is. So is it the total volume or the volume partial volume? Okay, sir.
So, week 7, right?
Yes, sir.
Lecture 17, is it?
Yeah, chapter 17.
Second problem, right? Additive pressure
Yes,
rule.
sir.
Okay.
Yeah, the last part. Yes, sir. The reduced volume.
The reduced parameter for CH4. Okay, the reduced volume for.
Yeah, reduced volume, sir.
So, what is the doubt you have here? How is
Sir,
the?
we have, yeah, yes, sir. The reduced volume has the general formula, as we know. But when we dealt with the case rule, we put in the specific volume of the system, which we calculated at the very beginning. But here we have calculated the specific volume for the component, and it has been written as V by N1. So I'm confused about it. Where we get this V, because is it the is it supposed to be the volume of the component? That is CH4. We have N1 that we did earlier, but what is V? So I tried putting in different values. I tried initially, like we calculate partial pressure, the mole fraction multiplied by the total pressure. I did that, but answer is not the same.
If I can mark here. So you mean this VR, right?
Yes, sir. The
So VR is
VR.
nothing but V1 times PC by R bar TC, right?
Yes, sir. It is.
And V1 is, it should be total volume divided by N1. So
Okay, sir. So
what are you getting? Is it not the right?
it's yes, sir. I was not getting because the total volume we can take
Case rule, we
0.24.
do this reduced parameter for a mixture,
Yes, sir.
and in additive pressure rule, we need to use the reduced parameter for each and every individual
Okay,
constituents,
sir.
right? Uh, so should be V, let's say, what is V? 0.24 divided by
Point one eight.
N1 is 0.18
One eight.
into C1, is it?
PC one So we can take it as 464 kilopascal. 64
4.
divided by R bar. 8.314 will be R bar, then multiply by 91.1. Yes, sir. I'm getting very different result.
I see. So R bar should be 8314. That's no problem. Divided by TC1. What is the TC1 you're looking?
191.1.
Getting around 0.389. So
Yes, sir. Exactly.
they are getting around 2.61. Is that your question?
Yes, sir.
Okay, okay. So what if you go forward with your results and find the pressure?
Sir, I didn't continue it because I was not sure about the formula. I thought I'm not getting something, I have missed something, and I did not continue. And also, sir, in the previous part, in the C part where we dealt with the vendor walls part, I have problem with the coefficients because the constant A, which was calculated, was getting a value here as 8.113. When I calculated it, it's coming as 2.848. So again, the result is totally different there as well.
I see. Okay. So Van der Waal coefficient, actually here what they did was they took it from the tables itself directly, coefficients. So you calculated using the 27 by 64, those
No, no,
number.
sir. Actually, when we use the van der Waals, we have to calculate the coefficient A or and B for the mixture by an empirical relation. It is y1 a I to
Okay,
the
okay,
power
that
by 2.
that one. Okay, okay,
Yeah.
okay. That is not coming.
Yes, sir. I'm not getting the same answer here as well.
They wrote to be 8.113 and I'm getting 2.848.
Yes, sir, exactly. I got the same. I calculated it further, and because it was simple calculation, and I received pressure as 95.18 bar. It's little bit higher, and earlier it was told that normally idle gas relation gives the maximum pressure.
I
But
think here the problem is here what you calculate is A power 1 by 2. So, if you look at the equation, let me write it down. A is y2 into a2 power 1.
yes, sir.
Here A, if you look at these units will not change. The reason is here it is
So,
in terms of square root, here it is in terms of 1, right? So ideally what
yeah.
I feel is it should be like this.
Okay, sir.
What
It
we
will be
calculate
square.
is a square root of a, which is 2.84.
Yeah.
Let's square it. How much you are getting? 2.84 and 11. Is that what they are getting?
Yes, sir. Exactly.
Haha. So I think that is a units problem. I think Sir wrote
Yeah. Yeah.
maybe incorrectly. It's a power half. So that is fine. Um, this part I will check and let you know. So,
Okay, sir.
so why don't you do one thing? You try to go forward with your results for UR
Okay,
and
sir.
VR and check what is
Okay.
the pressure you are getting. Maybe sometimes
Okay,
he
sir.
must have written, must have mistakenly wrote maybe some typo error. Maybe you
Okay,
can
sir.
check that once. Okay.
Okay, sir. Sure.
Also check that. So it's lecture 17, problem 2. Is there any other question, Amit, you wanted to ask?
That's all for now, sir.
Start our problems today. Um, I have four problems here. It's quite simple, and all are going to deal with the mixtures. Say if you have a two constituents in your system. Till now we deal with only pure gases and pure. I mean, only pure substances we dealt with. What if a pure substance goes through a process from process one to two? Here we have number of constituents within that substance. Okay, so the first question deals here with a rigid tank which contains 2 kg of nitrogen at 25 degrees Celsius and 550 kilopascal. It is connected to another tank which contains oxygen at 4 kg, 25 degrees Celsius and 150 kilopascal. Now if they open this valve, this two gases will mix, right? So if it mixes, what would be the final, determine the volume of the tank, you need to find also the final mixture pressure. Okay, simple and straightforward. um, just write given data, and temperature is 25 degrees Celsius, and I think mixture temperature is also 25 degrees Celsius, so it doesn't matter. 25 degrees Celsius means 298 Kelvin. Pressure in the tank 1 is going to be 550 kilopascals. Again T is same, pressure is 150 kilopascal. For the sake of completeness, I will write this one. First is to find volume of the tanks. Say N2 tank. How do we find the volume of this tank? Only you are here, so I'm going to ask you all the questions today.
Sure, sir, no problem. I think it's great to have a complete one-on-one session.
So um, you're free to ask me questions anytime. So how
Yes.
do we go forward?
Sir, we can get the specific volume, I guess, from data.
We could do from data also.
Or ideal gas equation would do as well for that.
It's better if we use ideal gas. It's easier in a way here.
Yes, sir.
One of the assumptions we are going to make, because ideal gas is not given in the question, right? So there's
Yeah.
no problem. Take ideal gas. So here I wrote in terms of mass, so this can be written in terms of volume. So volume is equal to mRT. So here everything is for N2. So it's going to E, or you can rewrite as universal gas constant divided by molecule of N2, right? Pressure P. So possible, can you quickly calculate and let me know?
Yes,
8314
sir.
times the weight of N2 is 28, I guess, into 5 into 10 power 3.
Sir, I am getting 0.322 meter cube.
In 322 meter cube. So I guess I didn't make any problems here, because this will be in terms of kg, and this will be in joules per kilomole Kelvin divided by kg per kilomole. Kilomole, Kelvin, kg. So joules per Pascal is going to be. So because I don't know whether you have gone through last class lectures and all, sessions and all, because it was so funny. I missed all the uh, you know the units, so I was getting weird answers, and then it took some time for me to uh, rectify my results. So that's why I'm being very careful over here. So let's say we'll calculate for O2 tank also. So this is VN2. Write it down here. VO2, which is going to be MO2 RUT. Mass of is 48314 into 298 is 32, right?
Yes, sir.
Pressure is 150 kilopascals.
So I'm getting 2.065.
2.066
2.065.
meter cube. Yeah, I'm also getting the same thing. All right. So this is volume of else we need to find out. We need to find out mixture pressure. Okay, let's find out that also. Think we can find it out. We need to find final mixture pressure.
So with ideal gas, we can use the Dalton's model, which says the total pressure is sum of the partial pressures.
Yeah. Okay.
But for that, we need number of moles, I guess, in each.
Let's find out
Yeah.
number of moles. Uh, since it's an ideal gas, so mixture is also going to be ideal gas because each and every gas is also ideal gas, right?
Yeah.
Temperature is known. So let's say if you write a equation PV is equal to MRT for a mixture. Okay. So will you be able to find it out? So we need to find the final pressure,
So,
right?
yeah, definitely.
So
Simple.
mixture RT divided by V of mixture. So this will be easier way.
Process.
You can even use partial pressures. Also should give you same results.
Sir, what should we write for R specific gas?
R, yeah. So R is going to be RU by molecular weight of mixture. So to
Okay.
find molecular weight of mixture, you need to know the mole fractions or number of moles of each and every
Definitely.
component. So anyway we need to know. So let's say if you uh, specify mole fraction to be yi, going to be molecular weight of y, which is nothing but mole fraction of n of n2 plus fraction of O2 molecular weight of O2. So for that, to find mole fraction, you need to know moles. How many moles of nitrogen and oxygen is present. So let's find it out how much moles. So let's say N2. Number of moles is going to be, we know mass of N2.
Yes, sir. Mass upon molecular.
It's going to be molecular weight of N2. So it's 2 divided by 28. There will be some kilomoles. Similarly, you can do for O2 also. Which is this coming out to be?
So N1 is 0.0714 and N2 is
0714.
0.125.
It is going to be kilomole. And this one 0.125.
125. And
You can calculate mole fractions. Y of n2 is going to be n2 by going to be 0.074714 divided by 0.0714 0.1. Similarly, you can calculate mole fractions of O2. It is going to be 0.125 divided by 0.0714 is 0. Which is this coming out to be
so it's 0.364.
0.364, and this is probably going to be 1 minus 0.364.
Yeah.
Right? Even if you calculate, it's going to remain same. So it's actually better to find mole fraction and find the molecular weight of mixture, because we deal with mole fractions in our combustion also frequently.
Okay.
So it's a good practice to find mole fraction. Without mole fractions also you could find the molecular weight of mixture, but it's fine. So uh, how much is the molecular weight of mixture? This is going to be 364 times 28 plus 0.363 times 32.
So it's 30.544.
30.544 uh, kg per kilometer. We found the molecular weight of mixture. Now you can find the R and you can substitute and you can find the pressure. So the total pressure is going to be mass of the mixture. Mass of mixture is nothing but mass of N2 plus mass of O2. Mass is not going to change upon mixing, right? And that is 8314 times it remains same, divided by molecular weight 544 into volume of mixture is also going to remain same, because it's going to be just V of N2 plus V of O2. Because those are rigid tanks. We already saw that, right? So since it's a
Yes.
rigid tank, we no need to, it's not going to change. So if that is the case, it's going to be 6 times 8314
Sir, is temperature, final temperature given in question?
Yeah, so if you look at here, the mixture temperature is also given. It's
Okay, sir.
25 degrees. So they are telling that after mixing also it's an rigid. So after mixing also the temperature remains same. That is what they are telling.
Okay, sir.
It's the pressure.
So I'm getting 203.89 kilograms.
203.89. Okay. Right. So yeah, and also it is in between 150 and 550 and 150 kilopascal. So
Yes, sir, it is.
let's move forward with the second question. In this second question, what we have is So people have already done a volumetric analysis, and volumetric analysis of mixture, what it gave was 30% oxygen, 40% nitrogen, 10% of carbon dioxide, and 20% of methane. So all these are by volume. So um, so there is a flow coming into this pipe, and that flow contains by volume this percent of gases, and the mixture is heated from 20 degrees Celsius to 200 degrees Celsius. I forgot to put degrees over here. Okay. And so what is our job is to determine the heat transfer to the mixture per unit mass of the mixture. So we need to find how much heat I need to supply to raise its temperature from 20 degrees Celsius to 200 degrees Celsius, and the pressure is remaining constant. So it's like uh, constant pressure heat addition process. But here it is a flow. There is a flow. It's not a closed system, it's an open system. So this again, we let's consider ideal gas for simplicity. And we need to find heat transfer, right?
So heat transfer would be change in enthalpy.
Basically, it actually comes from steady flow energy
Steady flow
equation,
energy. Yeah.
or it's a first law of thermodynamics. Both are same. Um, so heat transfer is going to be just simply change in enthalpy, which is nothing but Cp times T2 minus T1, right? So if that is the case, T2 and T1 are known. Only thing is we don't know Cp. Because since we have a mixture of gases, we need to find Cp mixture, right?
So here also we have, I think, assumed that Cp is can be taken as constant with respect to temperature.
So here we can assume that Cp is a constant uh, from T to 20 to 200, or you can get a good estimate of Cp, like a Cp averaged Cp or something like that. Maybe around, let's say, 100 degrees Celsius. What is the Cp? You can take that as a constant Cp, and you can go forward with the analysis.
Yes.
Yeah, good point. Let me write that down. Cp is constant. Whenever we write, it's automatically the assumption is Cp is constant. So this assumptions you should not make when you deal with combustion systems, because there it is the yeah, when you study about it, you will come to know this temperature flame, there will be adiabatic flame temperature, and it is more dependent on CPs of the product uh,
Okay, sir.
reactions. So yeah, let's so for this problem, let's assume that Cp is constant, and what we need is, but we need to Cp for a mixture. Now it is not a pure gas phase, it's a mixture of gases. So how do we find Cp mixture of gas? So this is per unit mass of the mixture we need to find. So it's better to take Cp in terms of uh, joules per kg Kelvin, right? So Cp mixture is in terms of mass basis. That is what I'm trying to say. Cp mixture should be in mass basis. How we should find the Cp of, how do we find Cp of mixture from the individual constituent Cp? Any idea?
So maybe taking the product of mass fraction and Cp of component and summing them all together.
Fractions, let's denote it as xi and Cpi. Okay. So basically, if you do this, you will get uh, the Cp of mixture. That is true. So let's if I want to extend and write this out, it's going to be x2 xo2 Cp m2 xco2 Cp co2 plus ch4 Cp ch4. So now we need to find x. What to find x is.
It would be mass of that component per unit total mass upon total mass.
But we do not have a mass of a component, right? We
Yes, sir.
have
We have
volume
total
of
mass.
components. It's true that it's mi by m total or m mixture. Find m i's and m mixture.
So from I think we can use the ideal gas equation for each component.
Real gas equation. Um, yeah, we can use it. What would happen is going to be uh, EV by RT, right?
Yes, sir.
By P V mixture by RT. Here it's going to be RI, here it's going to be R mixture, right? So P will get cancelled, T and T will get cancelled because individual constituents and the mixture is going to have same pressure and temperature. So if that is the case, then Vi by V mixture times R mixture by Ri we can write. So this also we can rewrite it as Vi by V mixture. So R mixture is going to be Ru by molecular weight of mixture, right? So then you can write molecular weight of mixture. So what we know is Vi by V mixtures we know, right? So that is what is given. Now we multiply by molecular weight of I by molecular weight of mixture. But one more thing, how do we find molecular weight of mixture? This is known because percentage by volume is given. This is also we know. How about this?
So previously we used the moles fraction. I
Right.
think
Huh. So
here we have the volumetric analysis.
right. So this um, by volume basis is actually equivalent to molar basis. So that is one thing you need to understand here. So Vi by V mixture is nothing but volume fraction, which is actually nothing but mole fraction. So whatever they gave here was mole fraction. Since you know mole fraction, you can actually find molecular weight of mixtures. So is that clear what I'm trying to say?
No, sir, I didn't get it.
Okay, so what we need to know is let's write it down. Molecular weight of mixture. Molecular weight of mixture is nothing but mole fraction of each and every I into molecular weight of I.
Yes,
So we need to find y of I. What is y of I? Y of I is nothing but number of moles of I divided by number of moles of
sir.
total number of moles in a mixture.
Yes,
This is nothing but Vi by V mixture. That is what I am trying to say. So let's say if you go forward with this analysis, so how do you if you apply ideal gas for Ni by N total, how will you do it? PV is equal to nRT, right?
yes, sir.
Uh, right? N is going to be PV by RT. Vi by RT. Similarly, this is also going to be PV mixture by V mixture.
Yes, sir. Exactly. Because yes, sir, the mixture, the pressure for mixture and temperature for mixture is equal to components.
Right. So These two are actually same. It is true. Pressure for mixture is equal to pressure of each and every gas.
Sir, is this because of the setup we are having, this open flow system?
So it is not because of that. So I think there is something called partial pressure, right? So that is different
Yeah.
than this. So here the whole mixture is going to experience the same pressure. The partial pressure is what is that constituent is contributing to that total pressure is what partial pressure is. So that is different than this one.
Sir, I think then partial pressure concept would be useful for closed system and not for open system.
You could say that. True. Uh, for open systems, its pressure is, yeah. For closed systems, it would be useful. Yeah.
So it is like that volume addition rule where we have a container with basically pressure and temperature, and we then do that.
Right. Right. So yeah, that would there also it would be helpful. Uh, yeah. People also do it when you have a exchange process happening, whether the evaporation will happen or not based on the local pressure, right? When the local pressure exceeds the partial pressure, then it can easily evaporate. I mean, it can boil. So that is one of the
Okay.
places where
At
people
lower
use it,
temperature.
right? So there also partial pressure, but basically the volumetric analysis is nothing but molar analysis, which gives us mole fraction. So that is the key takeaway from here. So if that is the case, then yi's are going to be easier. So it's already given in terms of percent. So you can write YO2, YN2, I think YCO2 and YCH4. 30, 40, 10 and 20. 10 and 20. 3, 4, 5. Mixture, which is going to be point 2 times CH4 is 12 plus 4 16 plus
42. Minus 20.
28
Minus 45.
44. Yeah. The molecule
So I'm getting 28.4.
is 28.4 kg per kilomole. So then yeah, so then we can find x size. So that was our aim.
Yes.
So uh, so x size are mass fractions. Let me write it down. I is our mole fraction. Mass fraction x size is going to be actually Vi by V mixture, which is nothing but Yi times molecular weight of I by molecular weight of mixture. This as Yi Mi mixture. Uh, if that is the case, we can find XO2 to be IO2 MO2 mixture 3 times in of N2 mixture divided by 28.4 mixture is going to So 44 divided by CH4 MCH4 divided by molecular weight of mixture. This point LCH4 0.2. 16 divided by 28.4. This
So I'm getting for oxygen 0.338, for nitrogen it's 0.394,
394. Okay.
so and for CO2 it's 0.6197. Yeah. And so for its point 2, it is 0.1127.
So I think CO2 is quite high. So if you add all these, it should come out to be 1.
Okay, so this is multiplied by 44 divided by 28.4. Yes, sir, it's 0.155. My bad. Yeah.
Makes sense. So now if you add all these, it will be 3, 3, 1, 1. I think.
Yes.
So now you can find CP of mixture. CP of mixture is going to be XO2 CP of O2 and N2 CP of N2 CO2 CP of C. Usual species you can take it from the tables. So
Yes, sir.
for now I have the data with myself. Let me write it down. 0.198 kilojoules per kg Kelvin and P of N2 is 1.039 kilojoules per kg Kelvin. If you want a good approximation, good estimate of CPs, it's better to take it in a average temperature. Let's say 20 plus 200 by 2, right? It'll be around 110.
Yes.
That would be the
So
better estimate.
can we use the Janak polynomials as well?
We could use Jano polynomial, but that is not a constant with respect to temperature. Right?
Yes,
So
sir. Then we have to integrate.
we should have integrated in the first step itself. It is better to deal with all those things in a computer without. So doing by hand is going to be very difficult with
So
those Jano
basically, sir,
polynomial.
we need to code it.
Right? Yeah. Basically, we should code it. Okay. So it is the CP of mixture we get.
Sir, do you mean that we should do the numerical integration?
So both numerical integrations also we could do, or you can even do symbolic integration because it's
Okay, okay.
a pressure, right? So it's a simple
Yeah,
integration, Cp
it's a
times T.
simple problem. Yeah.
Cp is also as a function of temperature. It's going to be a polynomial. Symbolically, you can integrate the polynomial, and you can do numerical integration. That is also easy, and that also will give
Sir,
you better results.
sir, these values I think are taken at 20 or 25 degrees Celsius. Values of CP.
I'm not exactly sure. I just took at random temperature, I guess. Probably at 20 degrees Celsius. I didn't go through the tables.
Okay, sir.
So, but it is better to take a temperature, 110 degrees
At it.
Celsius,
Yeah.
right? Because 220 divided by 2. Yeah. So it is better to take at 110 degrees Celsius and calculate this CPs. So, were you able to check for 110 degrees Celsius what is the CP you are getting?
Sir, I have to check with it. Sir, I have some data, and at around 110 degrees Celsius is 383 Kelvin. If we take at 400 Kelvin, the CP for CO2 is 0.939.
So it's better you take at 110 itself. So what is the you are getting CPs, CP values? Can you quickly tell? CP of O2 at
0.939.
110.
No, sir, CO2, not O2.
CO2, what is at 110?
0.939.
Okay, 110 means
383.
383 Kelvin. Okay, point 0.9.
Yes, sir, but I'm taking at 400 because of the data.
So 0.39 K. Is it kg per
kg
kilojoules per
per
kg
kg.
or kilomole?
It's kg per kg per kg.
Kg.
Per kg
Mass
Kelvin.
basis.
Yeah.
Okay. And CP of O2
So O2 is 0.949.
Kelvin. And N2
So N2 is 1.044.
kg Kelvin. And
And
H4
I don't have any data for methane.
can write, we can take whatever the data I have. But in NASA polynomials or Janov polynomials, you will get the data. That is fine.
Yes.
Say if you calculate it, how much you are getting. X of O2 is 0.338. These are mass fractions. Okay. Plus X of N2 is 0.394 times 0.1127. So how much is that you are getting?
So 1.1289
Kilojoules per kg Kelvin.
kg Kelvin.
That is the case. What is the Q will get? You get CP of mixture times T2, which is 200 minus T120. So 3 degrees Celsius. And what is that?
So shall we take it in Kelvin? The temperature?
But it's a difference, right? You can take it in Kelvin also or degree Celsius also. It's going to remain same. 200 plus. So it's 200 degrees Celsius minus 20 degrees Celsius. So it's a delta T we are talking about. In Kelvin also it will again give you 180 only. Right? 273. Right. Delta T's you can just simply substitute whether it is degree Celsius or Kelvin. That's not a problem. It would be a problem if you have a Fahrenheit. So that you should be careful.
Okay.
Is that you are getting 1289. Getting around 203. So you can check that. It's nothing but kilojoules per kg. That what you are getting?
Sir, yes, but if I take them in Kelvin, then I'm getting 511.39.
So 200 degrees Celsius, right? 200 plus 273 is 473.
Yes, sir.
Minus 20 plus 273 is nothing but 293. So 473
Yeah.
minus 293 is still 180, right?
Yes, actually, sir, I took the sum first and then I converted that, so that's why.
Oh, okay. So in delta T will remain same even if you take degree
Yeah,
Celsius. Okay.
and sir, it's also the case if there is division, T1 by T2.
T1 by T2 it's not the case, right?
Okay.
T1 by 2. So let's say T2 by T1 you do, which is nothing 200 by 20 is not equal to 473 by 293.
Okay, sir. Yeah.
So
Let me.
division you should not use. This is wrong. But in T2 minus T1 you can use. The reason is in T2 also you are adding by 273, T1 is also you are adding by 273. So there is a negative, it gets cancelled. So it doesn't really matter when you have a negative, when you have a positive sign also in between. For simple summations it will work. For multiplications and divisions it will not work. But it is best, it is better to use Kelvin scale itself. Let me just rewrite this also. Kelvin scale. It's going to be 473 minus 293. All right. So let's move on to next.
Sir, I had one question. Sir, is this, have you considered the assumption that the composition is uniform everywhere? Because, sir, we're taking,
So yeah, that is the composition is present actually everywhere. True, it's a uniform everywhere. So that is so if you look at it, this is a mixture, right? And these are miscible uh, mixture constituents. So as soon as it comes in contact, it mixes fully. That's why you can safely consider that it is uniform everywhere. Even if you don't consider, let's say, even if some part is O2, some part is 40, so if it is divided like this, anyway it is going to enter in as a some mixture and it is going to leave as a mixture. So for this problem, that is not a case, because we don't consider how it is distributed inside the domain. We are just considering how much it is entering, how much it is leaving, and what is the change in temperatures in between them. So this is like a black box where we no need
yeah.
to know what is the mixture constituent present inside. Only thing we know is whatever enters leaves with the same composition. That is what
So, yeah, so like typical macroscopic approach.
is true. And when you have a in this problem, that's not a problem. But your question is right. We usually consider mixture means it's uniformly present everywhere. So that we consider true.
One more thing, sir. By the start of the lectures, it was mentioned that we assume that the components are pure,
Hmm.
that they are pure substance. So does that mean? So basically, the whole mixture is some of the pure components.
Yeah, yeah, true.
Okay, sir. So can we say that the mixture itself is a pure substance?
Mixture is a pure substance provided it has a molecular weight, mixture molecular weight, and you know its number of moles. So, for example, air, right? You usually
Yeah.
consider air as a pure substance only. We
Yeah.
dealt with from previous lectures, right? So, but air has its own compositions like N2 and O2. So, this mixture is also a pure substance.
But that there, in case of air as well, we have the uniform distribution.
Right.
Because
There also we have
composition is same
uniform.
everywhere.
True.
Exactly.
So it is true, we can consider mixture is also as a pure substance, but provided the properties will change based on that. So Cp will not be in terms of N2 and O2, Cp will be in terms of air. So for an air, what is the Cp? And all these Cp's will be calculated based on this only. So whatever we did, so here we had this much percent of by volume. So basically there you will have 9 percentage of O2, 21 percentage of N2, and certain argons and H2O will be present in the air, right? On this only we calculate that CPs also. CPs, molecular weight, everything. It's constant, everything. So
Sir,
yeah, you can consider. Yes, go ahead.
sir, in practical situations, do we consider this assumption, uniform composition?
So it depends upon the field of view. Let's say, for example, you are interested in this kind of problems, whatever we dealt today, right? Then you consider uniform position. For example, let's say you have a combustor, okay, gas turbine combustor. Let's say.
Yeah.
Now, what happens? There will be a engine like this, gas turbine engine. So in aeroplanes, you must have known, and there will be a fan over here, and there will be some compressor over here, right? Which compresses series of blades will be the
Yes, sir.
compressor. Till and from here there will be the air will be coming out, and there will be small ports in which the fuel is injected, right?
Yes, sir.
So this fuel will be injected, and here the combustion takes place. And if you want to analyze what is happening inside, right, here you can't assume that fuel is present everywhere, air is present everywhere, and it is reacting. So that is not a proper way, right? So then you should consider separate streams. So fuel is coming out in here, air is coming out, fuel and air are mixing in over here, right? And then they form a flame, and then they after that be a combustion products coming out, fuel, air, and then products will be coming out, and then it exhausts through nozzle, right? So uh, if you want to consider what is happening inside, then you shouldn't say that composition is uniform everywhere, fuel is everywhere, you know, air is everywhere. That is not a proper way. At that time, what we use, there is we have this mass fractions, right? So what we do, we solve for this mass fractions. Let's say we will have a species mass conservation equations. So basically, we will consider how much amount of mass is coming out, and how much amount of mass is leaving, and how much has reacted, how much is unreacted. Those things we consider. So for that, there is something called species mass conservation equations. There, each and every uh, each and every space point in space, how much is y of fuel, y of air, and y of products, you will know, right? For that you will solve
So,
this species mass conservation equation.
so is it like the Reynolds transport equation where
Exactly.
we take the variation within the control volume?
Right. So in Reynolds transport theorem, what you do is you just take a control volume, uh, and what you do, you just uh, a, it is like a control volume approach. It's like an integral approach. Here, what you do is you do a differential approach. You will string this control volume to a point, and you will see how that varies along the each and every point. So basically, you can write a mass conservation equation, Reynolds transfer theorem like this, right? So you can write integral of dou by dou t. So this will be like uh, plus I think control surface
Control
integral
surface.
uh, v dot n d
Equal, yeah, D.
equal
Yeah.
to 0. So this is the integral approach, and in this case you don't consider what is happening inside, you see. So this part is 0 because system is 0, and you just consider how the volume changes, what is entering this control surface, nothing but what is entering and what is leaving, and this is what it is. But if you want to know what is happening inside, what you do is you take this differentiation inside into rho
Yeah.
integral of dv, and then you will apply Gauss divergence theorem, so that this becomes control volume integral. This is also volume integral. This is also volume integral. So this becomes a divergence of rho v into dv 0. Now this is the whole control volume, which is 0. So you can take it out outside, and this will be your mass conservation equation. So this is your mass conservation equation, and this you can apply inside everywhere. Everywhere this mass conservation equation has to be satisfied. So uh, similarly, you can find the species mass fraction, and you can actually track where each and every species is going. So that is what in CFDs we do this only. We basically solve this kind of equation. That's why we discretize the whole domain into small control volumes, basically meshing, and then we do this, right? So it
Yes.
depends upon the field of study where you are considering whether it is uniform or non-uniform. Right? In this same case, let's say you have a thing coming in. So what we did here was we told that 30% is coming in and 30% of O2 is going out, right? There is a possibility some of O2 can stay inside. Because of that, 30% O2 will reduce and N2 might increase percentage, right? Even though not any reactions happen, even if there is no reactions, and in addition, 30% of O2 the pipe, and then CH4 can come in the lower part of the pipe. That is also possible. And also this will be coming as a separate stream, and when it comes out it will be coming as a mixed stream. Those things are possible. But what we did was we considered it as a black box. We no need to know anything, so we just did this analysis, and we showed that it is a uniform everywhere. And it also depends upon what we are studying. We are studying about the mixture. We are not studying about each
Yeah.
and individual component, how it is changing. So in that cases, you can consider it as uniform, and you can just apply the this mixture properties there.
So, sir, we can say it's a homogeneous mixture we are studying.
Yeah, yeah, you can say homogeneous mixture. That is not a problem. Only problem is at this places it will not be accurate. You can still say this is my whole domain. My air will come in, and then fuel also will come enter like this, and this side there will be only products. You can still say this also, but only thing is you it would be accurate only if your control volume is outside everything, outside whatever the combustion chamber is happening. So let's say your control volume is here, and fuel and air is coming out. This here also there can be different things coming out, right? At this point it would become inaccurate to do that. Is that
Sir,
clear? Is
I
that
think
answers?
turbulence will also be present, and that will also impact
So
the mixing process.
turbulence impact. Yeah, yeah. So if it is not uniform, it's going to impact. It will get impacted by everything. The turbulence will impact. The reactions will impact. In fact, the important thing is diffusion, right?
Okay.
Each O2 and N2, if it will diffuse between each other. So O2 will be fuel will be higher here, and fuel will be lower in between these things, right? So fuel will diffuse, and air will go opposite, right? So that diffusion will affect the species, how uniform it is. True. So diffusion, so turbulence is main thing is diffusion. In
Okay.
addition, turbulence also will affect. So those are not, I won't say minimal effect, but major effect is diffusion.
Okay, sir.
Diffusion of species. Discussion. Let me just.
Sir, I
Yes.
think similar thing we can say for a diesel engine as well, because here
Yeah.
also
Ha, ha, ha.
we have
So
this.
in a diesel engine, until it enters inside, it will be a pure air, right? In a diesel engine,
Okay, sir.
and then you inject the fuel. So you will assume it's uniform, and you can do some simplified analysis, and you can get some performance out of it. But that performance would be lesser than the actual performance. The performance would be more than the actual performance. The reason is this whatever injected fuel will not be uniformly mixed inside the combustion chamber, and because of that your performance loss will happen. So that part you will not be able to. Those are some things you will lose when you consider it to be uniform. True.
Okay, sir.
All right, let's continue with the third question. Do you have follow up questions, Anish?
No, sir. That's it. Thank you.
So let's continue with the third question. A mixture of hydrocarbon gas is composed of 60% methane, 25% propane, and 15% butane by weight. This mixture is compressed from 100 kilopascal to 1000 kilopascal in a reversible isothermal steady flow compressor, and calculate the work heat transfer for this compression per unit mass of the mixture. So, um, in certain devices you can assume that assumption that it is uniform, like a compressor and like a turbine, assume that it is uniformly uh, mixed, but in combustor you cannot do that. That is something you can remember about. So in here, for example, we have a turbine. Basically this kind of turbine, do you have any idea where do we use it? So it's a compressor, sorry.
Sir, sir, in a power plant, I guess.
So in a power plant, power plant, what do we do? So in a power plant, what do we do is let's say steam power plant. Let's not go with steam power plant. Let's say in a gas
Yes,
turbine
power
power
plant.
plant,
Yes.
we have a working fluid as air, right? So in air we compress it, and then we mix the fuel and we'll burn it, right? So uh, that is also there also, but fuel we don't burn. If you look at it, these methane, propane, and butanes are fuels, right? So
Yes, sir. They are
basically,
getting compressed.
fuel is getting compressed is actually seen in rocket engines. Okay,
Okay, sir.
let's say if you take a liquid rocket engine, you will have a fuel compressor and you have an oxidizer compressor. You will carry your own fuel in that case, and then you have to compress it to a high pressure. The reason is, if you have a higher pressure in the combustion chamber, you are going to get more performance. That is the reason. So what we
Yes.
basically do is we will compress it to a higher pressure, and then we will put it in the combustion chamber. We will let it burn. Okay, so these kind of devices you will see in rocket engines, and there across the turbines you can assume that uniform mixture is uniform. Okay,
Okay, sir.
all right. So uh, have hydrocarbon gases, which is CH4, and one more thing is, last example we saw it's by volume. Here it is by mass. So
Okay, sir.
the volume, when we say by volume, we understand we found out that it's nothing but molar, right?
More fraction.
Mole fractions. Since it's by mass, it's going to be simply mass fractions. So we just write it down. So given m dot fraction, what do we use? X of CH4 is going to be zero point 0.6, and X of C3H8 is going to be 0.25, of C4H10 is 0.15. Okay. Mixture is compressed from 100 kilopascal to, so this P1 is 100 kilopascal, 1000 kilopascal. Reversible isothermal steady flow compressor. Okay, and the temperature is 20 degrees Celsius. So temperature is, it's isothermal, so temperature
Absolutely.
doesn't change. And so T1 equal to T2. What do we ask to find out is calculate the work and heat transfer of for this compression per unit mass of the mixture. So it's just compressor. How do we find work done by compressor?
So we should use the steady flow equation.
So the steady flow energy equation. Okay. steady flow energy equation, which is going to give us mcp, not cp, m times, right, cp times T2 is 0, right? So this will be 0
Yes, sir.
to H1 plus kinetic potential energy will be 0.
Yes, sir. Sir, I think
Yeah,
if
yeah, yeah.
you
So there will be heat loss also.
yeah.
W is equal to m dot H2 Q, right? So work you are giving to the compressor. So is this how it be right?
Yes, sir. Energy input is equal to rate of energy output.
Same. This H2 minus H1. So what this gives is actually, since T's are same, it just gives W is equal to Q. QN, right?
Yes, sir.
Which is nothing but Q. That is fine. Found the solution for second problem. Basically, you see, we need to find heat transfer also. We found out that heat transfer is nothing but work transfer. But what is work transfer? How do we find out? So we know a equation, right? Work done is going to be integral of,
We-
I think it's in second week, I guess. Nothing but PdV. And for open
Yeah.
system, you uh, I EH equal to du plus pdv plus vdp, right? And then
Yes,
when
sir.
you substitute it back, q will be dh, uh, this whole thing. So finally it will be du is equal to integral of vdp, something like that. Work done will be equal to integral of vdp.
Yes, sir. Yes, sir.
So now we have a mixture. So again we'll consider ideal gas. Let's say if you consider ideal gas mixture, PV is equal to RT. Here it is in terms of specific volume. So PV is equal to RT.
So we need
T is
volume
equal
as
to
a
RT.
function of pressure.
हाँ हाँ.
Yes,
Repeat, Amit.
yes, sir. I said that we need volume as a function of pressure so that we can integrate.
T by P into dP. And since R and T doesn't change because
Yeah.
uh, there's no, the constituents are not going to change. So, and isothermal. So it's going to be integral of 1 to 2 dP. So it's going to be RT by P1, right?
Yes, sir.
So if you write it down, so now you need to find, this is nothing but RUT by molecular weight of mixture. So only thing is you need to find molecular weight of mixture. This is P1, P2, P1 we know, T we know, RU also we know. We need to find molecular weight of mixture. So molecular mixture we already saw, it's going to be,
Mass friction into the
is it,
component.
isn't it mole fraction? It's,
Yes, sir.
but we have mass fraction, so we need to convert mole fraction to mass fraction. do that. It's so if you look at it here, the y is kg of I, sorry, not kg, it's a mole fraction, no? Kilomole of
Yes, sir. Hello.
I by kilomole of mixture.
Mixture.
It's kg of I by kilomole of I. Basically, what we are trying to do is kg of I by kilomole of I. Kilomole of mixture we are adding, we are summing up, right? And what we know is we know xi's are
Mass fraction.
kg of I by
Kg of mixture.
kg of mixture. We get to here. So let's say if you multiply xi uh, with
Into
molecular weight of I, right? The weight of I is kg.
mass of
So
I
you
upon
need to
volume.
divide by molecular weight of I. Let's say if you divide kg of I by kg of mixture, a kilomole of I by kg of I.
Yes, sir.
So you will get kilomole of I, kg of mixture. And then if you add all these things, you kilomole of mixture by kg of mixture. So when you add summation of xi by mi, you will get mixture by kg of mixture. And we know molecular weight of mixture is nothing but kg of mixture by kilomole of mixture.
Yes, sir.
Basically, what I'm trying to say is uh, this is nothing but you can also write this as molecular weight. So it's nothing but 1 divided by summation of xi by molecular weight of it. That is what I'm trying to say. You can also write this as summation of xi by molecular weight of it. Basically, both are interchangeable. Is that clear? It's just simple algebra.
Yes, sir. Algebra.
So, since or what you can do, you can just simply calculate mole fractions and then you can calculate the molecular weight of mixture. It is a very big process. Instead, you can simply use this formula. So these two formulas are interchangeable. That is thing you can remember. So if that is the case, so you can write 1 divided by x of CH4, x of CH4 by molecular weight of CH4 plus x of I think C3H8 and C4H2. C3H8 by molecular weight of C3H8 and x of 4H10 C4H10. Should that be? So weight of CH4 is 0.6. 6 divided by CH4 is 16. Okay. And this 0.25, right? C3H8, how much is C3H8? C3 is 12, 12, 12, 36 plus 8. It's 44. Okay.
Yes.
It's 44 plus and 0.15 divided by C4H10. 4 is at 58. What is the molecular weight of mixture you are getting? So you find that problem solved.
So it's 21.85.
1.85.
Yes, sir.
kg per kilometer. Then you can find work done, but in that 8314 divided by molecular weight 20. What is T we have here? T is 20 degrees Celsius. It's nothing but 1000 kilopascals by 100 kilopascal.
Yes.
Check that coming out to be. mm,
Sir, why did we take R for air?
Did we take R for?
Sir, we use R as 8314. No, sorry, this is R bar. Sorry, universal gas constant.
Yeah, yeah. This is RU by. So I
Yeah, yeah,
use
exactly.
yeah, okay.
This is R bar.
Is that coming out to be?
So it's 0.257 uh, megajoule.
Okay, 0.257 megajoules. I think it should be per kg, right?
Yeah.
So we found the work transfer. So heat transfer we already found. It is going to be simply same. This is going to be equal to Q. All right. Let's, we have one more final problem. I think this problem I think we already did, but for a pure substance where there will be spring loaded and it will um, constantly heating and then it will expand, right? Piston cylinder device contain a mixture of gas whose pressure fractions are. Now here we have pressure fraction. That is why I took. So last was mass and now it's pressure. Previous one was volume. So by pressure we have uh, defined into like we based on pressure we have three uh, constituents here. The pistons diameter and spring are selected for this device such that volume is zero point 0.1 meter cube when the pressure is 200 kilopascal and 1 meter cube when the pressure is 1000 kilopascal. Basically, they are telling that with respect to pressure is going to be varying like this. That's what they are telling. Initially, the
Sir,
initially
it is not partial pressure.
this one is that this one
Sir,
is
the pressure fractions are not partial pressure, I guess.
oh this is good question. This is actually partial pressures. So this is our pressure fractions. It is not really partial pressure. Okay. Let's say if you use partial pressure and if you use ideal gas, you cannot use partial pressure with the ideal gas law. Okay, these are pressure fractions. True, these are little different than partial pressures.
Yes.
Okay, so pressure fractions are 25%. Now, what was partial pressure? I got
Sir, Sir, when we use the Dalton's model, it said that it's very consistent with the ideal gas model because we do not consider in ideal gas the size of the molecule and also the forces it exerts within each other. So it's like if the component is there alone and it is having a pressure, and that will be the partial pressure.
So, so that component alone within the same volume, right?
Yes, sir. Within the same container, we'll be having the pressure that is partial pressure.
Partial pressure.
And
Okay.
if we add the partial pressure of all the components, we get the pressure for the whole container.
So, if that is the case, then this pressure fraction should be same as partial pressures, right?
Okay, sir.
You add all the pressures, you will get the final pressures. Basically, this pressure
No,
fraction is nothing but partial pressure.
sir, it is summing up to 100%.
So, it is same as partial pressures, true. All right. So, let's solve this also. Actually, the gas is added to the device until pressure is 200 kilopascal and the pressure is and temperature is 10 degrees Celsius. The device is now heated until pressure is 500 kilopascal. Calculate the total work and heat transfer for this process. Okay. So, pressure fractions. So the difference between this pressure fractions and partial pressure is in terms of pressure, but pressure fraction is in terms of partial pressure by the total pressure.
Okay, sir.
Understand?
Okay, sir.
So is that making sense? So here, let's say if you write E is 0.25, P of O2 is 0.5, and P of 2 is nothing but 0.25. These are pressure fractions. Okay. Now let's say if you want to find partial pressures of P of Ne, which is nothing but 0.25 times 200 kilopascal. Let
Hmm.
me put it as a small p. P of O2 is nothing but zero point 0.5 times 200 kilopascal. And the P of N2 is nothing but 0.25 times 200 kilopascal. That is a actually partial pressures and the pressure fraction. So this will
Exactly,
be
sir.
in terms of pressure units and pressure fraction is fraction.
Yes, sir. The units are absolutely different for those.
We find it. So what they are telling is we are heating the mixture, right? Mixture is initially at P1 is 200 kilopascals and P1 is zero point 0.1 meter cube. This the
Sir,
temperature at T1 is also 10 degrees Celsius and we are heating it, which means you are adding Q, and then P2 is 500 kilopascals they're telling. Then so some V2 is there, we don't know, and some T2 is also there. Since you are adding heat, its temperature is also going to change. Or we don't know what is the temperature change. Let's see.
yes.
So here we need to find this work done and heat transfer. What is this? What is the work done? And the work done should be simple, right? It's going to be simply PdV,
APU.
right? Integral of PdV.
Yeah.
One more thing is important thing about what they gave for a piston cylinder device is this is devised in such a way that let's say this is P and this is V. Uh, they are telling that device such that zero point 0.1 meter cube when the pressure is 200 kilopascal and 1 meter cube when Pressure is 1000 kilopascal. Let's say this is 200 kilo. Some other point 1 meter cube. Pressure is 1000 kilopascals. That's what they are telling. Be varying in some other manner.
So it will depend upon the spring. If it's a linear spring, then I guess it will be linear variation.
True. Yeah. So let's say if it's a linear spring. So the pressure is going to linearly vary, right? So since pressure varies, force varies linearly, the pressure also will vary linearly. So
Mm.
basically, we are heating till only 5000. We are heating till only 500 kilopascal. So this is our point two. So one is this V we need to find out. This is going to be our V2.
Yes.
In this, it's going simply area under this curve is going to be the work done.
Yes.
So without going through all the mixture properties and all, before itself we can find this out. So since this varies linearly, you can simply find V2 also. Right? So V2 is going to be uh, this slope. So slope is going to remain constant.
Constants.
So say how do we find out? So V minus V2 divided by V2 is equal to so this 1 and 2 is independent of this. That's it. Let's mark this as 3. Okay. Since 3, 2 we don't know, only 3 we know. So you can substitute V2. V2 minus V3 divided by V1 minus V3 is equal to P1 minus P3. Right? You can find V2. V2 is the 3 divided by P1 minus P3. So
Yes.
let's say if you do this, is that clear? Did I go too fast?
Yes, sir.
Well, it's going to be 500 divided by 1000 times V1 minus V3, which is 0.1 minus 1 plus 1. Is that coming out to be?
All right.
1 minus divided.
Point five five.
0.55, right?
Yes. Meter.
Oh, sorry. It's okay, I did 500. No? So it's actually P2 minus P3 is 500, but P1 minus P3 is actually 800. No?
800. Yes.
1000 minus 200 is 800. Sorry. By 8 times 0.9. So is that around 4375? I'm getting
Yes, sir. It is.
75 meter cube.
Meter.
We already found V. V2 is also found. P2 is also we found. So we can simply go for area
So this is the trapezium.
trapezium, or you can find the area of this triangle and then square. You can add it these together.
Yes, sir.
So I don't remember trapezium area formula right now. Probably I will go with the traditional method. So do you remember what is the trapezium formula?
Sir, it's one half into sum of the bases multiplied by the altitude.
Okay, multiplied by the altitude. So it's you are telling is V1, V2, is that you're telling?
No, sir. I think it is yeah opposite, sir. I think we should add the pressure and then multiply it by the change in volume.
Change in volume. Okay, V2 minus V1. Okay. 2 into P1 plus P2 is going to be 200, which is 700 kilopascals times. Write it in terms of 3, and then just that convert to be
That will be 8.125. 118.125. Usually.
we found work done. Without getting into this mixture, we found out work done.
Yes, sir.
This is also 0.375 meter cube. We need to find now heated until pressure. Calculate the total work done. We need to find heat transfer during this process. Heat transfer. If you want to find heat transfer, we have to use.
First law.
There's no other. Yeah, there's no other option. We have to use first law. We go about. Law is going to be change in internal energy is
Enter.
equal to Q minus W. W is no. Q is what we need to know. Del U W. Del U is MC
Yes, sir.
1, right?
Yes, sir.
W. Picture things.
Yes, sir. For specific heat.
Mass is given. Is the mass is given? So mass is not given. Mass also we need to find out. The mass of this you know system, and also
Yes.
we need to find CV also for this mixture. So we find out. Mass is you can again assume ideal gas. Ideal gas mixture and ideal gas constituents. Say if you do that, neon is going to be PV is equal to P, right?
Yeah.
PV is equal to MRT. So P into V. So with neon, and this is, as I said, it's going to be partial pressure. So then if this is the case, partial pressure we know it's going to be 0.25 times 500. So V, what is V? We know temperature at initial
Yes,
state,
sir.
right? So let's use initial V itself, 0.1. 8314 divided by an argon neon, huh? So probably 20. Oxygen, oxygen, fluorine, neon. Just checking. It's a neon. 20.8. Sorry, 20.18 times temperature is 20 degrees Celsius, right? That's what. Sorry,
Yes,
10 degrees Celsius. So it's going to be 280
290, 80.
reverse mass of neon. Similarly, oxygen and nitrogen. Partial pressure of O2 V by 16. Partial pressure of O2 is 5 into 500 into 0.1314 divided by 283. Nitrogen. Nitrogen is going to be by R of N. It's going to be 0.25. Oxygen is 28. Other masses coming.
It's 1.072 into 10 to the power minus 4 for neon.
1 point.
072 into 10 to the power minus 4.
Oh, okay. Let's take again. So it's not 500, it's 200. So can
Yes,
you
sir.
quickly do?
Because we took volume at V1. At one. That is,
I wrote 200, but I instead there I wrote 500. And we took the state one, right? So that's why it should be
yes, sir.
200. Sorry about
So but mass
T2,
would be of course same for both of the states.
but we don't know the T2, right?
Yeah. Yes.
So we cannot use 283 there. So that is the problem. If you use 200, you need to use 283 Kelvin.
Yes. Sir.
So, so 1 point something you said. Can you quickly do multiply by 2 by 5?
So it's 4.2884 into 10 to the power minus 5.
4.2 into 10 power.
It's a 4.29 into 10 to the power minus 5. So I'm getting 29, 4.29.
Sorry, 4.2 names. Sorry. 4 point. Probably I think it should be, since it's kilopascal, it should be multiplied by 10 power 3. So maybe it should be minus 2.
It said we are taking the gas constant in joule.
Yeah, it's in joule.
And
So
yeah,
that
that is
also,
why we have to multiply by 1000. Yeah.
so we have to multiply by 1000. True.
Yes, sir. Exactly. And, sorry.
So then it would be 10 power minus 2, right?
Yes, sir. It's exactly 0.043. Point 136.
6 kgs. Wonderful. Nitrogen. How about nitrogen?
It's 0.09595.
0.095.
595.
595. Okay.
Yeah,
595 kgs.
yeah.
All right. So mass is done. We need to find CVs. Uh, so to find CV, what we know is we need to multiply by mass fractions, right? Xi into CVI. The total mass we know. Total mass is nothing but mass of neon, mass of nitrogen, and mass of O2.
Oxygen.
So then, if that is the case, if you add all the masses, how much is it coming? 0.936, 0.059.
0.2385.
0.2384 kgs. So this is the total kg. Now we need to find out mass fractions of each and every uh,
Yes, sir.
constituent so that you can get the CVs. So let's say x of Ne, it's going to be
No, sir.
of O2 is going to be which is it coming to be around
0.18.
okay. And then how about this?
0.57.
Is going to be simply 1 minus. So is that 0.25?
24. Yeah, 0.4.
0.25. We found mass fraction. Now we need to find CV. CV should be at a temperature. So what we could do is we need to find at which temperature we need to find that we don't know. We can find at T1, but it is better if you find in between, right? For an average temperature. For that we
Yes.
need to know T2. So how do we find
So, ideal gas equation.
T2? Yeah, wonderful. So we can use PV is equal to, right? Okay. T2 is
Yes.
equal to P2 and V2 divided by mass into R. In molecular weight of mixture, did we found already? No. Be Ru times molecular weight of mixture. In molecular weight of mixture, in last problem we solved in terms of mass fraction, right? So that is
Yes.
nothing but of xi by molecular weight of I. Let's use that itself. 1 divided by x of Ne by molecular weight of Ne plus x of O2 by molecular weight of x of N2 by molecular. Is the case, it's going to be 1 divided by 0.18 divided by neon is 20.18 plus O2 is 0.05 divided by N2 is 40.
Yes, sir. 28.07.
58.07.
7.
Okay. Kg per kilo.
Per
The molecular weight of mixture is known, R is known, M is known, so we can quickly find out P2. P2 is P2, it is 500 kilo per 30 into 10 power 3. V2 is we found out how much was it, 0.
0.55. I guess.
4375
Yeah.
75, and molecular weight of mixture is 28.07 whole divided by 0.2384. Mass is not going to change as you said,
Yes, sir.
and 8314. Which I'm getting very high value. Is that what you are
Yes,
also
sir.
getting?
3097.95.
7 kelvins. This is too much. I don't know. Let's find out how much Q we need. Okay, so T is done. So if T is done, then you can find a picture where you can find the CVs. So it's going to be T1 plus T2 by 2, which is plus 283 divided by 2. Maybe at average temperature of 1690 Kelvin. At 1690 kelvins, you can find CV of Ne, CV of OT. So maybe in the interest of time, I will give you the values what I have with me.
Okay,
Uh,
sir.
Not sure whether it is taken at 1690 Kelvin. You can check it out. But it is better to take at average temperature.
Yes, sir.
So 8 joules per kg Kelvin and 0.743 kilojoules per kg Kelvin. So if you put it in together, then you can find CV of mixture to be uh, 0.672 kilojoules per kg Kelvin. It's just repeated calculation. I don't want to bore you.
Okay, sir.
CV is done, so you can simply find. We just found the equation. Q is nothing but mCV T2 minus T1. Q is M is 0.2384 times CV is 672 times T2 minus 31 297.9 minus 283. I into 10 power 3, because since I wrote this in joules, I need to write that also
Yes,
in
sir.
joules. So how much is the Q coming out to be? Okay. So is it around 500 kilojoules? 569 I'm getting. 69
Yes, sir.
kilojoules. How much joules is required in order to pressure and volume from 200 to 500 kilobar? It's like 2 bar to 5 bar. This much. I don't know why the temperature is too high. Maybe because of this is the answer, right? That's all. So you do a lot of work you have to do in order to calculate any gas mixtures. So that's why people what they do is they use softwares to do most of the work, or they make their own programs in MATLAB or something, and they calculate all these things easily. So there is also one software called it's a open source. You can link it with MATLAB and use. There's something called Cantera. You can give it a try if you're interested. Only this you can the going forward you will learn about combustion, and you will be learning about equilibrium temperature, adiabatic flame temperature, mixture compositions. So all these things you can do it on your hand, but it's a very lengthy process and it requires a lot
Yes,
of
sir.
calculation, and you will end up having arithmetic mistakes. So it's better to have a program, and the program will run and give you the results. So this Cantera is one of the open source software. You can use it for it's in Python, and I think you can also download in MATLAB and use it in MATLAB also. So you can use it for mixtures and all. Let's see if possible. I will show the demo once this combustion things comes. I will show a demo of Cantor also if you are interested.
That would be
Once.
great, sir. Sir, are there tutorials available on online for Cantina?
Yeah, there are tutorials. If you look into the website itself, if you just search for Cantera and the website itself, you will have certain tutorials. There will be Python scripts will be available, or MATLAB scripts will be available. You can go. But you need to know little basics about combustion in order to go into that. So that's why after
Yes, sir.
certain concepts are uh, taught, we can see how it works with Cantor also. Maybe I will show you a demo.
Okay, sir.
Right? So is there any other questions from the audience?
Sir,
Yeah.
when will you upload the slides, sir? I actually wanted to write the questions.
My slides, you mean this one?
No, sir, the questions only, or even the link, if you could upload it in a couple of days. I don't write the questions, I just go with the answers.
Oh, okay, okay. No problem. Yeah. See, basically, I usually upload everything at the end of the class itself. You know the drive link, right? You have the drive link, right? You
I
have the
think
drive
it
link?
is it in the website?
Sheets. It's in the Google Sheets. So, do you know where the Google Sheet is? So, in the website, let me show you.
Okay.
So, here you get problem solving session July 2023, right?
Yeah.
There there will be problem solving session recording. If you click that, uh, it will open a Google Sheet. Okay,
Yeah.
Google Sheet. I usually upload everything. Uh, so there is this presentation folder link, right? In this,
Mm.
you can go to this drive and you can see all the things are here. So I will upload this also right after the class. Okay. I mean,
Okay, sir.
we also have another audience here. Vishal, do you have any more questions? Do you have any questions to ask?
No, sir.
Thanks, Vishal. Thanks, Hamid. We will see in the
Okay,
next
sir.
week. Sorry for taking extra 5 times, 5 minutes.
No problem, sir. Thank you.
No problem, sir.
Vishal, bye, Hamid.
Goodbye, sir.